Let's now generalize what we did in the last video. So if this is my y-axis, and this is, that's not that straight. This right over here is my x-axis. And let's say I have two functions. So I'm just going to say it in general terms. So let's say I have a function right over here. So let's say it looks something like this. So that's one function. So this is y is equal to f of x. And then I have another function that y is equal to g of x. So let's say it looks something like this. So y, the blue one right over here, is y is equal to g of x. And like we did in the last video, I want to think about the volume of the solid of revolution we will get if we essentially rotate the area between these two, and if we were to rotate it around the x-axis. So we're saying in very general terms, this could be anything, but in the way we've drawn it now, it would literally be that same truffle shape. It'd be a very similar truffle shape, where on the outside it looks like a truffle, on the outside it looks like something like a truffle, and on the inside we have carved out a cone. Obviously, this visualization is very specific to the way I've drawn these functions, but what we want to do is generalize at least the mathematics of it. So how do we find a volume? Well, we could think of disks, but instead of thinking of disks, we're going to think about washers now, which is essentially the exact same thing we did in the last video mathematically, but it's a slightly different way of conceptualizing it. So imagine taking a little chunk between these two functions, just like that. What is going to be the width of this chunk? Well, it's going to be equal to dx. And let's rotate that whole thing around the x-axis. So if we rotate this thing around the x-axis, we end up with a washer. That's why we're going to call this the washer method. And it's really just kind of the disk method, where you're gutting out the inside of a disk. So that's the inside of our washer, and then this is the outside of our washer. Outside of our washer looks something like that. Hopefully that makes sense. And so the surface of our washer looks something like that. I know I could have drawn this a little bit better, but hopefully it serves the purpose so that we understand it. So the surface of our washer looks something like that, and it has depth of dx. It has depth dx. So let me see how well I could draw this. So depth dx, that's the side of this washer. So a washer, you can imagine, is kind of a gutted out. It's a gutted out coin. It's a gutted out coin. So how do we find the volume? Well, once again, if we know the surface, if we know the area of the face of this washer, we can just multiply that times the depth. So it's going to be the area of the face of the washer. So the area of the face of the washer, well, it could be the area if it wasn't gutted out. And what would that area be? Well, it would be pi times the overall, the outside radius squared. It would be pi times the outside radius squared. Well, what's the outside radius? The radius that goes to the outside of the washer. Well, that's f of x. So it's going to be f of x is the radius, and we're just going to square that. So that would give us, this expression right over here would give us the area of the entire face if it wasn't a washer, if it was a coin. But now we have to subtract out the inside. So what's the area of the inside? What's the area of the inside? This part right over here. Well, we're going to subtract it out. It's going to be pi times the radius of the inside squared. The radius of the inside squared. Well, what's the radius of the inside squared? Well, the inside in this case is g of x. It's going to be pi times g of x squared. That's the inner function, at least over the interval that we care about. So the area of this washer, we could just leave it like this, or we could factor out a pi. We could say it's equal to, the area is equal to, if we factor out a pi times f of x squared minus g of x squared. Minus, I don't really have to write a parentheses there, so we could write f of x squared minus g of x squared. And then if we want the volume, let me put that in that same yellow. If we want the volume of this thing, we just multiply it times the depth of each of those washers. So the volume of each of these washers are going to be pi times f of x squared minus g of x squared. the outer function squared over our interval minus our inner function squared over the interval, and then times our depth. Times our depth. That'd be the volume of each of these washers. Now, and that's going to be defined at a given x in our interval, but for each x at this interval, we can define a new washer. So there could be a washer out here and a washer out here. And so we're going to take the sum of all of those washers and take the limit as we have smaller and smaller depths, and we have an infinite number of infinitely thin washers. So we're going to take the integral over our interval from where these two things intersect, the interval that we care about. It doesn't have to be where they intersect, but in this case, that's what we'll do. So let's say x equals a to x equals b, although it could have been this could have been a, that could have been b, but this is our interval. We're saying in general terms, from a to b. And this will give our volume. This right over here is the volume of each washer, and then we're summing up all of the washers and taking the limit as we have an infinite number of them. So let's see if we apply this to the example in the last video, whether we get the exact same answer. Well, in the last video, y equals g of x was equal to x, and y is equal to f of x was equal to the square root of x. So let's evaluate that given what we just were able to derive. So our volume, I'll do it up here, the volume is going to be the integral. Well, what are the two intersection points? Well, over here, once again, we could have defined the interval someplace else, like between there and there, and we would have gotten a different shape. But the points that we care about, the way we visualize it, is between x is equal to 0, x is equal to 0, and x is equal to 1. That's where these two things intersect. We saw that in the last video. Of pi times, what's f of x squared? F of x squared, square root of x squared is just x, minus g of x squared. G of x is x, that squared is x squared, and then we multiply times dx. So this is going to be equal to, we can factor out the pi, 0 to 1, x minus x squared dx, which is equal to pi times, let's see, the antiderivative of x is x squared over 2. Antiderivative of x squared is x squared over 3. X to the third over 3. And we're going to evaluate this from 0 to 1. So this is going to be equal to, I'm running out of my real estate a little bit. Let me scroll over to the right a little bit. So this is going to be equal to pi times, well, when you evaluate this whole thing at 1, you get, let's see, you get 1/2 minus 1/3, 1/2 minus 1/3, and then you subtract it evaluated at 0, but that's just going to be 0. 0 squared over 2 minus 0 third over 0 to the third power over 3. That's just all going to be 0. So when you subtract out 0, you're just left with this expression right over here. What's 1/2 minus 1/3? Well, that's 1/6. This is 1/6. And so we are left with, this is equal to pi over 6, which is the exact same thing that we got in the last video, and that's because we did the exact same thing that we did in the last video. We just conceptualized it a little bit differently. We generalized it in terms of f of x and g of x, and we essentially conceptualized it as a washer, as opposed to kind of doing the disk method for an outer shape and an inner shape like we did in the last video.